Hello, everyone. We'll get started in just a moment here. All right. Thank you, everyone, for joining this morning, and welcome to this webinar series, synthesis workshop series on perceptual models of dominant hydrologic processes across North America. Before I hand things off to our speakers today, I wanted to give a brief overview of Quasi while we're getting started and folks are logging in. My name is Julia Masterman. My pronouns are she, her, and I am the Education and Outreach Specialist for Quasi. Quasi is the consortium of universities for the advancement of hydrologic science. We're a nonprofit funded in part by the National Science Foundation, and our mission is to empower the water science community and advance science through collaboration, infrastructure, and education. We fulfill this mission in a few main ways through our data services and then our community services. Our data services provide tools and support for the entire data lifecycle from data discovery through collaboration and all the way to publication. Quasi hosts 2 data repositories for water science data, primarily HydroShare. The hope is that by providing the support and infrastructure, Quasi can help researchers formulate and execute their data management plans, be effective data stewards, and meet the requirements of funding agencies. The other side of our organization are our community services. These include grants, workshops, a summer institute with the National Water Center for graduate students, webinar series and events like this one, a virtual university, and more. This is the third in the series of 5 workshops with morning and afternoon sessions. We hope that you'll consider joining us for the other workshops in the series and this afternoon as we discuss this morning's talks. Or if you have colleagues that are specializing in other regions, share the word that this workshop is going on. So today's workshop will focus on cold regions. Thank you so much to all of the conveners for putting together this series of workshops and to CIROH who supported this project. This morning, we'll hear keynote presentations from our 3 fantastic speakers. I'll be handing the mic over to Martin in just a moment to describe this project in more detail and to pass on the mic to the speakers. Thank you for taking the time to join us today and to contribute your expertise to the synthesis activity. This afternoon, we'll be hosting a synthesis discussion where we'll dive more in to this region and perceptual models associated with it. You'll need to register for it separately if you haven't already. The connection information will then be shared to you via email. We look forward to seeing and chatting with you in those meetings. A few logistics as we get started. This webinar is being recorded and will be posted on the Quasi YouTube channel. As an aside, the afternoon session will be recorded, but those recordings will not be shared publicly. Secondly, we ask that you use the Q&A functionality to submit questions to our speakers. Feel free to add questions at any time and upvote any that are especially of interest. We'll do our best to get to as many as we can. Finally, we expect that all involved with Quasi events uphold the Quasi Code of Conduct and promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you. With that, I will pass the mic on to Martin.
Okay, thanks, Julia. Let me just share my screen. Put in slideshow mode. Seems to be pretty slow this morning. Here it is. I assume that you can see my screen okay? Yep, looking good. Okay, excellent. Okay, well, thanks everybody for coming. Just wanted to follow on a little bit from what Julia mentioned and provide a little bit more details about the project. The need that we have is that when we're interested in predicting threats to water futures, and we need comprehensive models. The challenges that we have to quantify sustainable water supplies, water-related hazards, and understand the role of water in the Earth system. That these challenges can often exceed the capability of entire modeling groups, entire agencies, and in many cases, entire nations. And a community approach is needed to address some of these key challenges. The National Water Center in the United States of America has been building the National Water Model to address some of these questions. The initial versions of the model were relying on Earth system modeling approaches, where a land model was applied on a 1 kilometer grid, terrain routing applied on a 250-meter grid, routing on the NHT Plus river network, a level pool reservoir model. In terms of the prediction ecosystem, there was some parameter estimation at gauge locations with limited regionalization, data assimilation based on direct insertion. The advance is that it was providing information for about 2.7 million river reaches, extending the predictions from the 3,600 points that were served by the river forecast centers across the country. The critiques of this hyper-resolution paradigm were first that the hyper-resolution models don't necessarily perform that well because there's not sufficient information and computing resources to infer the large number of model parameters. And second, the hyper-resolution models aren't sufficiently agile to simulate observed processes in specific regions. So the National Water Center in the United States has been pushing forward the next-gen paradigm under the leadership of the NOAA OWP Chief Scientist, Dr. Fred Ogden. The motivation for the next-gen paradigm is that the siloed approach to hydrological modeling does not adequately consider the diversity of hydrological modeling approaches at various levels of spatial and process complexity. And it's difficult to identify a single model that's best everywhere, best at everything, and best all the time. So the solution, the approach that they're applying is to construct a deterministic multi-model mosaic that can represent the diversity of hydrological processes across the North American continent. If we're to do this, we need to know the dominance of processes in different corners of the continent, so synthesis is needed. So these are the challenges that we're addressing in this project. Land hydrology is incredibly diverse across the continent. So we need to understand what are the key forces driving hydrology: climate, vegetation, soil, geology, land use, direct water manipulations, etc. And then use these to try to provide a synthesis of the processes that are dominant in different corners of the continent, trying to understand what processes matter, where they matter, when they matter, and how the processes operate. This project is funded by the Cooperative Institute for Research to Operations in Hydrology. This is a new cooperative institute that's headquartered at the University of Alabama under the leadership of Professor Stephen Burian. The CIROH project is focused on research to operations in hydrology, bringing together contributions from government, academia, and industry to pull together domain science, computer science, and data science for the betterment of science, science for society. Part of the key mission for CIROH is to help the National Water Center improve its operation. So in this part, it is engaged in helping the National Water Center develop the next-gen water resources modeling framework. And as part of that in this project, to understand the theoretical underpinnings of models, that can be applied across different corners of the continent. So our goal then is to define the dominant hydrological processes for a continental mosaic of distinct hydrological landscapes. And the research that we're doing here is to iterate on producing a continental map of hydrological landscapes defined through the juxtaposition of hydroclimate, terrain and geology, vegetation, land use and management, and define or develop perceptual and conceptual models for each landscape in the hydrological mosaic. And the idea is that the synthesis that we're developing here will provide the theoretical support that's necessary for next-gen developers to simulate the salient processes and features of each unique hydrological landscape across the North American continent. So the team members that are included here, Hilary McMillan. So Hilary has dedicated a lot of her recent career to providing a catalogue of perceptual models across the globe, trying to provide a synthesis of those perceptual models to improve our understanding of hydrological processes globally. Hilary is from San Diego State University. Ying Fan from Rutgers University. Ying is well known for her synthesis efforts in the hydrological sciences, having completed a number of really important synthesis papers on plant rooting depth, on wetlands, on hill slope hydrology, etc. So we're very pleased to have Ying as a leader in this project to provide the synthesis that we're developing here. Katie van Verkhoven is our private sector partner from RTI International. She's working a lot on the transition of research to operations. So Katie's role in the project is to help ensure that what we're doing in this project has got relevance for future instantiations of the National Water Model. Wouter Knurben is a senior research associate at the University of Calgary, and he's been spearheading a lot of the research in this project, doing a lot of the work to define unique hydrological landscapes across the continent. We're also very fortunate to have our partners at Quasi, Jordan Reed, the Executive Director of Quasi, who's been a force of nature to drive through a lot of what we're trying to do here in these workshops. Julia Masterman, who introduced us here, standing in front of Aorangi in the South Island of New Zealand, and Irene Garusi Najad, who you'll hear from today as we're pushing forward on a lot of these issues. So as Julia mentioned, this is our third workshop in the Northern region. Our goal, to recap, is to improve the theoretical underpinnings of hydrological models by synthesizing process understanding across large scales and refining initial perceptual models through community workshops and focus regions. We'll have some meetings at AGU after all of these workshops to begin to refine a lot of the perceptual models that we're developing here. Of course, this is difficult. I see that Jeff McDonald's on the call here, and Jeff has been an active voice in our community to encourage us to move beyond the idiosyncrasies of individual hill slopes and try to begin to generalize results to large domains. The concerns that we have is it even possible to generalize hydrological behavior given the unique character of individual basins? Do we lack the necessary information to develop powerful and exceptionless explanations? And are the problems of underdetermination so pronounced that we can't move beyond explanatory pluralism, multiple explanations for the processes across different corners of the continent? But we think that we're at a point where we can make a lot of effort and a synthesis effort to systematically formulate, organize, formalize, encode, and evaluate hydrological theories. The community's made a lot of advances over the past few decades in our capability to explain and predict individual processes, process interactions, patterns, and scaling behavior. A lot of these process explanations are currently scattered across research groups and are not yet widely incorporated in hydrological models. So that's the purpose of these workshops, to begin to bring these process explanations together. And that we think it's possible by doing that, by unifying process explanations across watersheds, that we'll be able to make the advances in hydrological modeling across large geographical domains, that we need to make here. So I'll end there, and I'll stop sharing my screen. And then I will pass the mic to Sean Kerry. Sean, are you able to speak?
We're still working on getting Sean set up.
Okay. Okay, then I'm going to pass the mic to Michelle Wellford. Michelle, it's wonderful to have you join here. I've worked with Michelle in an editorial capacity, actually, when I was editor-in-chief for Water Resources Research. I was working closely with Michelle as an associate editor, and Michelle was wonderful in providing a lot of the authors with sage advice that helped them improve the quality and impact of their papers. It was really wonderful to work with you in that capacity, Michelle. Michelle has been one of the big thinkers in northern regions. She's published a few synthesis papers in permafrost landscapes. The key one that I know that I read and refer to a lot is the synthesis paper that you did with Barrett Kuralik a few years ago. So Michelle, it's wonderful to have you here. Michelle is a scientist at the United States Geological Survey, and we're looking forward to what you can share with us on perceptual models of permafrost landscapes in interior Alaska. So Michelle, thanks so much for accepting the invitation, and I'm really looking forward to your presentation.
Great, thank you, Martin, and thank you for the invitation. Can you see my full screen here, the full slides?
Yep, it's awesome.
Okay, great. So yeah, I do want to acknowledge the fact that a lot of the material that I'm drawing from in this presentation is from published work that I've led or contributed to. Just because I had that at the ready is not to say that there hasn't been a lot of work done by others, and there certainly has informing the perceptual models of this region. So I kind of apologize for not being more comprehensive and inclusive in that sense, but we'll give you something to chew on here. Okay, so let's see. Trying to get rid of. Okay. All right, so beginning with some of the basics. One of the most important components influencing hydrogeology and hydrology in interior Alaska, and certainly unique to cold regions, the more general topic here is frozen ground, right? So on the left is a vertical subsurface profile illustrating an active layer at the top that seasonally freezes and thaws. This seasonal cycling is further illustrated by the time series to the right, showing seasonal thaw within the dashed contour. Let me pick up a laser pointer here. So yeah, showing the seasonal thaw with depth within this dashed contour over the course of 2 annual cycles. And from a hydrologic perspective, ice in the pore space impedes infiltration. The active layer is on the order of tens of centimeters to a few meters thick in interior Alaska. And then below this, permafrost is ground that remains at or below 0 degrees for at least 2 consecutive years. Here again, pore space, ice in the pore space impedes water movement. The permeability of permafrost is very low. It's typically considered impermeable. And in interior Alaska, permafrost thickness, where present anyway, ranges from a few meters to about 100 meters or even thicker as you move northward. And so due to the contrast in permeability between frozen and unfrozen ground, you can start to imagine how the spatial distribution of each might control how water is stored and drained across these landscapes. So then moving to 2D in cross-section, this top figure represents a system characterized by continuous permafrost, defined as greater than 90% spatial coverage, where most of that subsurface water flow that's interacting with surface water bodies is in the active layer or the suprapermafrost aquifer. And talics, which are unfrozen, perennially unfrozen zones that develop around water bodies due to the thermal energy of those water bodies, they tend to be closed or not connected to an active flow system. It's a huge generalization, but There you go. And then this bottom figure shows a thicker suprapermafrost aquifer in discontinuous permafrost, defined as 50 to 90% spatial coverage. And that allows for deeper flow paths in the system, enhanced transmissivity, as well as a higher likelihood of open talics that allow year-round exchange between the subpermafrost aquifer and large lakes and rivers. So zooming out and looking in map view here, this mapped the mapped continuous zone or greater than 90% coverage lies to the north in the state of Alaska. Discontinuous permafrost zone covers much of interior Alaska, and that generally coincides with the boreal forest ecoregion. So that's kind of where I'm focusing this talk. Of course, we recognize that these permafrost affected systems are not static through time. And that same graphic that I just showed could be thought to represent the same system as it evolves through time with warming. This sort of change in the hydrogeologic framework with time really sets the stage for profound changes in how water is distributed and partitioned above and below ground and how water moves across the landscape. Permafrost thaw is occurring at differing rates, which I'll touch on later, but certainly over time scales that are of interest for hydrologic modeling projections through the end of the century. There have been several large-scale studies applying different methods to project major changes in permafrost distribution in Alaska. What I'm showing you here is just one example by Neil Pastick and colleagues. So this left map displays the current distribution of near surface permafrost represented in terms of probability, with the cool colors having the highest probability of retaining near surface permafrost. And then these maps on the right constrain the end of the century projections depending on different assumptions and climate forcing. The main point here is that major changes are expected over the remainder of the century, though there is uncertainty in the rates of change. Exactly what this looks like. Different modes of permafrost thaw will have variable effects on surface and subsurface hydrology. And so we'll just kind of quickly step through these, as they may or may not be important to represent in large-scale hydrologic models, depending on your model resolution, your timescales, and your modeling objectives. Okay, so stepping through, thickening of the active layer that seasonally freezes and thaws. That can deepen flow paths, allowing more water to be transmitted through the suprapermafrost aquifer on a seasonal basis. And then with continued warming, this seasonally active layer actually thins. The seasonal frost layer becomes more shallow, and a suprapermafrost talic develops. You can think of this as kind of a thaw sandwich during the winter. And if laterally continuous and connected to unfrozen water sources and sinks, these suprapermafrost talics can continue transmitting water year-round with implications for streamflow hydrographs. And then complete loss of permafrost occurs over both land and surface water bodies. That occurs over longer time scales, but the opening of potential subsurface pathways can facilitate surface water exchange with deep subsurface groundwater. In this particular example, the hydrologic gradients result in groundwater discharge to the stream. But this process can also result in kind of the opposite direction, groundwater recharge from an upland lake, for example, to a downstream river or additional lake. And then particularly in areas with high ice content, these ice-rich permafrost areas, the transition of ice to liquid in the pore space and the volume reduction that accompanies that phase change can result in significant ground subsidence, loss of geomechanical stability, leading to massive erosional features pictured above, the formation of bogs. And I don't have time to do justice to the array of these processes, but they can be very important in regions underlain by ice-rich permafrost and occurring over timescales of interest. From Landsat imagery, we infer that surface water distribution in interior Alaska has changed over time and that those changes are not uniform. Some areas are becoming wetter, shown in blue. Some areas are becoming drier, shown in red. And we hypothesize that the story is not just about increases in ET, changes in precipitation, et cetera, but also due to changes in the subsurface plumbing that is evident across very large scales. So for example, we have evidence of shifts in aquatic exports integrated over the entire Yukon River Basin, shown here to the left, that drains much of interior Alaska, specifically reductions in the dissolved organic carbon exports normalized to discharge. And that shift is best explained by subsurface water moving through deeper flow paths with longer residence times for decomposition. These deeper flow paths are presumed to be a reflection of large-scale permafrost thaw. This is a study performed, 2 decades ago, but I think it sets an important stage and concept of deeper flow paths, more water moving through the subsurface as the result of permafrost thaw, presumably. And then this concept was further supported by the streamflow trend analyses in the Yukon River Basin that documented pervasive multi-decadal increases in base flow in the Yukon River Basin in the absence of notable change in annual discharge. So not a lot of change in annual discharge. So just again, we have more water being routed through the subsurface over time, increased base flow. And as a groundwater hydrologist, this finding is what really got me excited about working in these dynamic landscapes. So I should stop here and just note that although frozen ground plays a big role in how water is stored and moved across interior Alaska, there are many other factors at play, and it's probably past due in this talk to acknowledge the very large gradients that we do see in terms of climate, topography, surficial geology, vegetation that span interior Alaska. It's a very diverse system that is difficult to generalize in a few perceptual models. But I do want to highlight an influential paper by Tor Jorgensen and others that provides subsurface perceptual models of 4 major boreal landscapes in interior Alaska with some attempt at extrapolation, kind of shown on this map. So the 4 classifications, and I'll show the perceptual models in the next slide. Those 4 classifications include rocky uplands, represented by some of the brown features on this map, silty uplands in yellow, gravelly sandy lowlands in orange, and peaty sandy lowlands in green. Okay, so here are the 4 classifications, and we'll just step through those one by one. So the rocky uplands are characterized by ice-poor hillside colluvium. In these settings, rapid permafrost thaw has occurred sort of post-wildfire, in response to wildfire, and it results in a pretty well-drained system with some relatively deep groundwater flow paths as well as super permafrost flow. Again, very well-drained. And then the silty uplands, in contrast, are very characterized by very ice-rich loess, fine-grained material with ice wedges, massive ice, which makes it fairly resistant to thaw due to the thermal energy that's required to melt these massive ice wedges. But when it does thaw, this system is an absolute sloppy mess, right? Fine grain material, thaw slump, erosion. But at current, not a lot of groundwater flow in the system, saturated soils, and near surface flow predominates. Moving on, the gravelly sandy lowlands are characterized by ice poor aeolian sands deposited over overlying fluvial gravels. Lots of lakes and ponds in many of these lowlands. Open talus beneath the large ones, so good potential for vertical groundwater surface water exchange through open talus, but limited lateral connectivity in the system due to the presence of existing permafrost. Because of these permeable materials, when thawed, this system is going to change dramatically, and I'll talk a little bit about that later in the talk. And then lastly, PD silty lowlands with a thick ice-rich peat deposits overlying reworked lowland loess that is rather not impermeable, but low conductivity, low permeability. We see in these systems an undulating topography resulting from about 2 to 4 meters of thaw settlement, with very fragmented drainage patterns, isolated thermokarst bogs, sort of a fill and spill flow, really, again, a focus on near surface flow processes. So I think this will be a really strong figure to return to this afternoon. I'll just put that out there. But moving on, the Yukon Flats Basin, shown here in pink, within the Yukon River Basin encompasses all 4 of those major landscapes types that I just mentioned. So it's been kind of interesting to study. And it also spans the transition between continuous and discontinuous permafrost, which happens to be a very interesting one from a groundwater flow perspective, as highlighted by these groundwater modeling results that show as we transition from continuous permafrost coverage, sort of this leftmost, to discontinuous permafrost, there is a potential 5-fold increase in base flow resulting from the enhanced groundwater circulation in the basin, and just an increase in the percent groundwater in total stream flow. So just underscoring this point here that the spatial extent, depth, and thickness of permafrost matters. It affects base flow, it affects the hydrograph. And yet, the deep boreholes that would provide that kind of information on permafrost distribution are few and far between in interior Alaska, or at least that we have access to. And so airborne geophysics has been able to fill in some of those gaps for us in informing the hydrogeologic framework. What I'm showing you here are some results from 2 airborne geophysical surveys that were flown across the Yukon Flats to develop resistivity cross-sections, some of which are shown here. Just very briefly, the high resistivity values, the cool colors, correlate to frozen material, and the low resistivities, these warmer colors, relate to unfrozen material. The underlying lithology in the system also influences resistivity, so we can begin to put together a more robust picture of the subsurface, including open and closed talus and how they relate to rivers, streams, lakes of various sizes and depths in the region. We do find open talus beneath the Yukon River and large lakes, and that's in line with the gravelly sandy lowland perceptual model in the Jorgensen paper. We also see evidence of these thick ice-rich permafrost loess plateaus in line with the silty upland perceptual model. We also see a lot of pretty deep, thick, frozen gravel. And that's really interesting as a hydrogeologist, because when that thaws, that's really going to alter drainage in this very lake-rich lowland. And though data from the airborne geophysics can be very useful for informing deeper patterns of permafrost and other hydrogeologic features, it's generally of limited use for characterizing the active layer or the super permafrost aquifer due to the coarse resolution. And so for shallow purposes, ground-based geophysics, including electrical resistivity tomography, which is shown here, that's been very useful for us for getting this more shallow picture. And here we see evidence of super permafrost talus that have developed with some lateral connectivity to streams. There's mounting evidence from others as well of super permafrost talc development, including new talcs across interior Alaska in response to rising temperatures, increasing summer rains. And so what might that mean for stream flow? This is we did a variety of generalized hill slope hydrologic modeling with seasonal freeze thaw and a long-term warming trend imposed upon it to kind of show how the development of super permafrost talcs, if laterally connective to an active flow system, can affect groundwater discharge to streams. Most importantly, we found that the talc development can result in increased total base flow magnitude and extend shoulder season base flow. Of course, there are many factors that influence talc development and thaw rate under a moderate atmospheric warming trend. Just highlighting a few here in this graph that shows thaw rate on the y-axis through time, x-axis, in relation to a base case, which is the solid black line for comparison. We see that a reduced snow scenario and a thick organic layer, these two lowest curves, those scenarios suppress thaw rate because there's less ground insulation in the winter for the low snow case. There's more ground insulation during the summer with the thick organic case, resulting in cooler soil temps overall. And then in contrast, the two highest rate curves are for the scenarios with the reduced summer shading, reduced vegetation canopy, and a thin or no organic layer. So collectively, these modeling results show an order of magnitude difference in projected permafrost thaw rates for rather subtle differences in snow, vegetation cover, and organic layer thickness. And this is important because that high sensitivity to vegetation, to shading, to organic layer and snow, that translates to permafrost vulnerability to wildfire, which is widespread across much of the boreal region. Wildfire, again, reduces canopy shading in the summer, reduces the thickness of the organic layer, depending on the fire severity, but reduces that organic layer through combustion and reduces the canopy interception, potentially leading to more snow accumulation, all of which can lead to warmer soil temperatures and, as many studies have shown, statistically significant deeper active layers. In some cases, fire effects on permafrost are pretty subtle and transient. In other cases, fire effects have been shown to be quite substantial. And on the more extreme end of that more substantial spectrum is a site south of Coldfoot, Alaska, near the continuous to discontinuous permafrost transition. It was partially burned in 2004. We started monitoring it in 2016. And plotted above here are the volumetric liquid water content obtained from borehole NMR. It was taken at the burn site to the left compared to the unburned site to the right. We see that liquid water content remains high at depth, shown in this pink area beneath the burned area for all seasons, including the winter. This is clear evidence of a superpermafrost talc. And in contrast, no talc beneath the unburned area. Then to supplement and extend those 1D findings, GPR was collected during the winter of 2019. Those results are shown here with annotated interpretations. These data indicate that talc extends to depths of 4 to 5 meters below the surface and extends across the burn scar. So this comparison rate of permafrost rate of thaw corresponds to about 20 to 30 centimeters per year. That's a very high rate. That's higher than we would have expected for this pretty cold site with a mean annual air temperature of -8. And that prompted us to further explore the role of wildfire as a catalyst. For talc development. And so we did that using a coupled thermal and hydrogeologic model. Just in brief, this modeling showed that combustion of the organic layer due to wildfire and changes in energy balance parameters associated with a loss of forest canopy could in fact result in rapid talc development extending 4 to 5 meters below the surface over the 15-year simulation in agreement with the field observations. And, just for context, this kind of thaw rate outpaces the current core scale talc projections under, the highest warming scenario in this area by about 100 years. So certainly large scale models cannot possibly represent conditions at every, okay, I think I need to go a little faster. They can't represent field conditions everywhere, but given the fact that wildfire is so widespread in interior Alaska and fire activity is projected to intensify and expand in the future, we do think that wildfire as a catalyst for talc development may need to be considered, or at least ask the question in large scale studies. And then I just have 2 more slides, wrap up slides that may be useful for continued discussion in the afternoon, in addition to those Jorgensen upland lowland diagrams. On the left here is my late Friday afternoon first cut at a list of important processes that influence how water's stored and moves through landscapes in interior Alaska. I've touched on some of these better than others during the talk. Maybe I've set my the other speakers up for expanding on some of these, but these apply to many other cold regions as well. And on the right, wildfire climate infrastructure, primary drivers of cold region processes, list of some of the important factors that control the hydrologic impact of the processes on the left. Again, happy to come back to these later in the afternoon. And then this last slide is my kind of lazy attempt at summarizing many of the processes and concepts that I've described in my presentation. It's kind of lazy in the sense of them already being published figures, though I did contribute to both of the development of both of them. There's a lot of overlap between the two. This left graphic contrasts an ice-rich landscape with thermokarsting and massive buried ice on the left, with an ice poor discontinuous permafrost landscape on the right with more subsurface connectivity. And then this right graphic illustrates continuous to discontinuous spectrum from front to back, conveys some of the effects of warming from thaw towards the right side. I do acknowledge that a more ideal perceptual model summary slide would incorporate the 4 main Jorgensen landscape types into this diagram, but given limited time and limited artistic skills, perhaps more importantly, I could not make that happen. So I think with that, I will stop sharing my screen and invite questions.
Thank you so much, Michelle. That is really, really wonderful. And I don't think you should stop sharing your screen. You probably, we're going to have some questions. People might come back to the screen, so you can leave your presentation on. So we are open to questions now. You can either type your question into Q&A, or I think the participants can type their questions into the Q&A, and the panelists can use the chat box. That was really excellent talk. This is from Martin. That was excellent, Michelle. Thanks. Michelle, maybe you can put your slides back a little bit. And you were saying, okay, here's a question that came in. I'm going to read this question from Anthony Prusil. Are there any studies looking at how soil hydraulic parameters may change with disappearance of the permafrost?
So the question is, how will soil hydraulic parameters change with permafrost thaw? Yeah, there's been a lot of studies that have been, looked at some of these soils in the lab and shown how permeability or hydrologic conductivity changes as a function of ice content, or changes as a function of temperature. And there are differences between how that looks in terms of sand curves, in terms of silt curves, fine grain, coarse grain, that sort of thing. There's analogies to soil moisture curves, how hydrologic conductivity or permeability changes as a function of air versus water content. An additional factor on top of that is that in some of these ice-rich materials, some of these materials that are permafrost is formed as the deposits are forming. It's called syngenetic permafrost, and that has so much ice in the pore space, it exceeds the porosity. So you would have a very different, hydrologic conductivity, developing a lot of sort of collapse. And so that's another element, the geomechanics that, I try to stay a little bit away from, but, is very important. And I don't know if that answers the question or not, but.
Okay, and next,
Yeah.
Thank you, Michelle. Next
Yep.
question comes from Martin. Can you talk more about the impacts of river ice on subsurface processes?
I don't want to take away from Benoit's talk, but I'm happy to do that. One thing that we've been interested in the Yukon Flats is how ice jam flooding contributes to prolonged flooding in this area, that in turn kind of changes some of the connections of lakes near the river. It thaws permafrost, creates some subsurface conduits. So these lakes near the river that have been kind of isolated, kind of acting in isolation, are now hydrologically more connective through time after some of these major flooding events. And that's due to the fact that you have these lakes sitting on top of pretty permeable material. So when thawed, there is a lot of connections that can just change the drainage in those sort of systems. So that's one aspect of the river ice processes that I was particularly thinking of.
And I'm sure Benoit will have more to say about it later. And the next question from the audience, from Habib Rahman. And what impact the climate change has on flood magnitudes from the cold regions? Flood magnitudes.
On flood magnitudes, yeah, I think this is really pointing towards Benoit's interests and talk in terms of flooding. You know, I think that there's been a bit of discussion in the literature as to whether or not flood frequency and intensity may increase or decrease in these areas in the future. In one sense, as you have more water that is being routed through the system deeper, increased groundwater flow, that can kind of sort of mediate the hydrograph, kind of cause higher, you know, higher winter flows, and potentially also create more thermal energy in these rivers in the winter that has the effect of thinning ice. So there's that aspect. But as you have sort of sharper increases in spring warming temperatures, you might expect the river ice breakup to be a little bit more dramatic, causing potentially an increase in ice jam flooding. So I think you could argue it both directions. And I would be really interested to hear Benoit's take on that as well later this morning.
Next one from Walter. When we are thinking about these increasing connections between the surface and deeper groundwater, do you have any thoughts on how much this would affect evaporation?
Yeah, I guess how this would affect evaporation in terms of the expansion or shrinking of some of these lakes. Is that
surface and groundwater connection, would that change evaporation?
Yeah, I mean, certainly as you have more exchange with these systems and you have a change in the surface area of these large lakes in either direction, that's going to change the potential evaporation over these lakes, the bare evaporation of these lakes. Yeah, I think changing surface area is kind of the main driver there. And we do see a lot of fluctuations in these lakes. And in the Yukon Flats, those changes are not uniform. They're not all shrinking. They're not all expanding. It's quite a mosaic. We've tried to kind of tease out some of those patterns in connection with the talic distribution beneath them that we can that we see in the airborne geophysics. We've made some relations there. We've kind of built some perceptual models in that Ray et al. GRL, I think, or no, ERL paper from 2019. I didn't really get into that a whole lot, but we do try to build some relationships between the directionality and changes in those lake area changes with their talic configuration and potential connection to the deeper groundwater system, as well as some of these more lateral shallow connections through time.
One question from Martin. A lot of your maps were for Alaska, for example, the Jorgensen's et al. Synthesis. Can you talk more about the geographic extent of these landscapes as we expand the geographic domain into Canada?
Yeah, I think that's a conversation not just for me, but for others. I think that there are certainly some extrapolations that can be made, and not others. There are a lot of peat landscapes that have some similar translation. The gravelly sandy lowlands are a little bit more unique, I think, to Alaska. I'm really intrigued by those areas just because of the potential for so much change in those systems as we move forward through time. So yeah, I think that's a great question to discuss as a group.
I think Sean will also talk a little more about, extending more toward east. We have time for one more question. Mohammed had two questions. I'm just going to read one of them. I was wondering how you see generalizing parameters to a larger watershed, as different subcatchments will have different response to runoff. I'm referring to infiltration parameters, depression, storage, etc.
Okay, I agree with that comment. What was the question in there?
How you see generalizing parameters to large watersheds?
How do you see generalizing parameters? With caution, as always. Yeah.
It's a good question.
It is a great question. It's a great question.
We struggle with scaling up processes. Lots of the processes, the fundamental processes, the scales are very small. So we struggle with that question. I think we're running out of time for questions. And thank you. Let's give a round of applause to our speaker, Michelle. Martin, the floor is yours. Thank you, Michelle.
Yes. Thanks. I just wanted to check that, Sean, you're able to share your screen.
So can you hear me?
We can hear you. Perfect.
All right, so I will try. I've never done this before. This is very exciting. I'm on my iPad. There's a share content. It says screen. Hold on, I could probably do this. Screen. Start broadcast. Just 1 second, and then I'll go to my.
Oh, look at you.
Okay, so when I there's the thing is what do you see right now?
We can see your screen broadcast.
Okay, and then so I think now I can probably get my PowerPoint open, and then we can go from there. Can you see that?
It's not yet. It looks fantastic. Look at you.
Okay, so can you see that? As I say, this is all new to me.
Oh yeah, no, it's terrific.
Okay, thanks, Martin. Thanks.
Can I introduce you first before you?
Sure. There we go. Trauma's over.
Yeah. Okay. Very good. So Sean's a professor in the School of Earth, Environment and Society at McMaster University. He directs the Watershed Hydrology Group. His research interests include hydrological and land surface processes in natural and human impacted environments, and he's got a particular interest in processes that are affected by cold temperatures and working in northern environments. And when I think of Sean, I think of him as a Yukonite. I think you've probably spent 30 years in the Yukon doing that's what it says. Doing field research. He's been a key player in work in the Wolf Creek research watershed that I had the pleasure of visiting a month or so ago. When I see Sean present to students, I see that he's got some very compelling perceptual models of the hydrological processes that are dominant in northern environments. So I'm really looking forward to your talk, Sean, and thanks so much for joining us.
All right, thanks, Martin. So I think you can't probably see me. You can just see the screen. So I will, sort of work my way through this. I'm really actually happy I went after Michelle because she did laid a lot of the groundwork that sort of I can kind of not sort of have to go through. And this is kind of a bit different because it's a bit more of my story and some of the things that I think probably large scale modelers should think about that sort of I've thought about over the last 30 years. Field process hydrologists sort of cause problems that modelers have to solve. So I'm just going to talk about some of the problems that I see and that I've caused over the last 30 years. And it's, again, going to be a bit more of a story and with just some old pictures and insights, and try to wrap it up on time. I want to show a map just sort of where I think this applies to. It's an overly generous geographic domain from Wolf Creek that Martin talked about, which is near Whitehorse, to a new watershed in north of Dawson in the Tombstone Mountains. And most of the Yukon's pretty mountainy and upland. There's some lowlands. It's not as much as Alaska. And so that's sort of the area. Some of the work may apply to the Brooks Range, which is a little colder, but I've been there a few times, but certainly that's sort of the area that I want to sort of generalize through the headwaters of the Yukon. Not really any glacial watersheds, though, and headwater lakes. Okay, so this is where I'm going to talk about my two homes, the Tombstone Water Observatory and Wolf Creek. Wolf Creek has some discontinuous to sporadic permafrost, where the Tombstone has much more continuous to discontinuous permafrost. Various from ice rich to ice poor. So the conditions are very variable. And I just want to say also the geology of the Yukon is extremely heterogeneous. Michelle talked about geology mattering. Geology of the Yukon, there's more variability in Yukon geology essentially than the rest of Canada, causes all sorts of sort of confounding factors that we still struggle to sort of layer over some of our conceptual models and perceptual models. Most of the perceptual models I've developed come from Wolf Creek. Historically, where my students and I have been working for a long time now. It's sort of an alpine, it's not sort of super mountainous, it's coast mountain, so a few thousand, maybe 12, 13, 1400 meters of elevation. And it goes from a boreal forest at the lowlands to sort of tundra at the top and high elevation and no permafrost at the bottom to lots of permafrost up top. So we sort of use a space for time or a space analogy toward different environments. And we've been looking at just sort of runoff processes and entire catchment processes and geochemical processes and land surface processes over a long time. So it's a bit of our study bed, and it was set up by a fellow, Rick Janowitz, along with John Pomeroy way back in 1992. I didn't arrive till 95. So it's, again, sporadic permafrost, different land cover types, again, forests, open tundra, taiga, buckbrush, which I'll talk about, and some alpine. So this is sort of the setting where a lot of the sort of, just to get you a feel for where it comes from. We work also a lot with First Nations. It's something I want to mention. A lot of the work we do in Canada's North is in partnership with the First Nations, and they've really support our work quite a bit. So if you actually go to Wolf Creek, there's a campground there, and with sort of some of the research and stuff translated into Southern Shoshone, and that's sort of interesting. So here it is in the winter. Here it is in the summer. That's the fall. So you get a kind of idea. And the one thing I want to say about working in these environments, maybe I think I saw Tyler DeYoung. He may have taken this photo. I saw him on the call. Working in these environments is a real challenge. And so some of the data and models that we come up with are based on, let's put it this way. I saw you had Jamie Shanley on last week. We don't have the Hubbard Brook level of infrastructure or people, so it makes it a bit more an adventure. The other site to talk about a bit, where some of the findings and sort of perceptual models come from, are the Tombstone Waters Observatory, which again is farther north, much more continuous permafrost in a lot of spots. It's sort of different alpine catchments we've set up, and we've been doing that since late 2018. It's where instruments go to die. It's extremely sort of fascinating and harsh environment to work in. And it's basically, it just chews up instruments and spits them out. And again, I think that's Tyler skiing down a mountain, which is kind of fun. And it takes a village. It's sort of lots of people have contributed to this work. It looks like these animals are looking at some of our snow stakes, but this isn't really just all, again, mine. A lot of these slides are brought in from students and folks that I've worked with through the years. So I just want to acknowledge that. I've been working there for 30 years, and there's been lots of changes that I've seen, and it's one of these things where, in the environment I live in now, seems to be the same for the last 30 years, but the North is changing pretty rapidly. This is an old slide. It says changing precipitation, forest scrub expansion, altered flow chemistry, thawing permafrost. It used to be reduced snowpacks, but there's a lot of snow, and there's almost more snow than there was before, it seems like, but I'll talk about, again, that as I move through. So what we see confuses us. So anything that sort of I see sometimes is just my bias. So hopefully you folks see other things. I always show this slide. I ask students what this is. It's a picture I took in the Tombstone Waters Observatory or near there. And people think it's the wall from Game of Thrones. And if you go closer, it's an inversion. So again, there's lots of things we see that are just sort of our perceptual. So this is just my story. We've thought about runoff processes and flow processes a lot actually through the years. I think it's largely been ignored what we've done in some ways. Way back in 2008, Bill Quinton, who was a close colleague for many years, and I wrote an opinion piece, I suppose, on a hydrological process. And we wanted to kind of highlight that although other runoff processes that sort of people are looking at in different environments, say Hubbard Brooks, where many would be developed, in other areas, Jeff McDonald sort of is very famous for synthesizing many of these. The one thing that we wanted to highlight is that it's heavily influenced by snow storage and release, permafrost and frozen ground restricts drainage, as Michelle mentioned. And the third one is the water holding capacity of organic soils, which I'll talk to that again. And again, other things like aerodynamic roughness, snow water equivalent, and sort of landscape redistribution and radiant energy. These were things that weren't really part of the sort of hydrological sort of zeitgeist in the sort of the 1990s when we started doing a lot of this work, is when we were doing our PhDs. So we wrote this opinion piece, and I think maybe it's been cited once or twice. So again, my Yukon adventures began in 1995. We don't do this anymore. They dropped me off in a helicopter. I had to build a little camp, which you saw down there, built a tent floor, and I lived basically 3 or 4 years for months at a time in this research watershed, sort of making observations and installing instruments and looking at sort of integrated catchment science processes. And the first thing that we noticed when we were flying around the basin, and this is one of the first photos I have, is that in subarctic mountain landscapes, aspect matters. And I mean, it matters a lot. And when we were setting up sites and looking at sort of representative catchments, we immediately noticed that north and south facing slopes were different in vegetation and soils and permafrost extent and runoff. And this was one of our first kind of ideas that, the equivalent latitude concept sort of like really strung itself sort of into reality in an environment like this, simply because of, if something is 10 degrees face north or 10 degrees face south, it can have equivalent climate influence of 40 degrees latitude. So that was kind of fascinating. I encourage everyone to read papers of Hawk Wu. Hawk Wu was my supervisor. He was Chris Spence's supervisor and many other people's supervisor. He's one of Canada's foremost cold region hydrologists, but his work really didn't make a splash. It certainly did in Scandinavia and Russia, but it really didn't in the US. It was sort of before the internet. But he spent years and years and years sort of mentoring students working in cold environments. So this is me smoking my pipe at, 20-something years old in my tent. And Hawk would translate what we found in the field into diagrams. He was actually like an artist, and he would sort of sit you down in his office and yell at you like people used to yell at students. And then you would translate your knowledge that you found in the field into conceptual models. And this was one of the first conceptual models that we developed out of my PhD. And it's simply trying to highlight the influence of aspect. And so there's a picture of Hawk. And I looked for his picture online, and I found this picture from when he first went to the high Arctic in 1974. The fellow beside him is Tim Burt, and I think that almost looks like fashion hasn't changed that much in how many years is that? 50 years, which is kind of funny. But yeah, these environments are drier than you think. I mean, Whitehorse only gets, 250 to 300 millimeters of precipitation at lower elevation in areas that don't have permafrost. It's a lot of silts, a lot of coarse grained material, and water tables can often be below the stream. They can be losing reaches. So we observed in these kind of dry south-facing aspects, just a lot of recharge, a lot of groundwater recharge to deeper aquifers, more deciduous forests, but sometimes these slopes would all be free of snow months in advance of streamflow being generated in the spring once the snow melted. In contrast, when we look at permafrost underlain slopes, we saw this progression from winter to summer, where snow would melt, and then there was sort of lots of flow and lots of stream flow timed well with the slope runoff generation from these hill slopes. There were, descending water table, descending frost table, and sort of a real link between these areas of permafrost and the signals that we saw in the stream. And again, we just worked to develop these conceptual models, which students look at now and think that that's all you did for your PhD. But yeah, that was it. To look at these sort of kind of different layered systems and preferential flows, et cetera, et cetera. And, when we're looking at simulating runoff, these sort of layered systems and kind of a variable boundary is really important as the active layer thaws and the frost water table descends atop it. And as it thaws, water moves through soil layers of different hydraulic properties, which I'll talk about briefly in a second. So this was the idea. It was sort of artistic and conceptual. and that sort of aspect really, really mattered. And then above that, layering on what aspect kind of resulted in, one being permafrost or not permafrost, other being vegetation type, which I'll kind of finish off, and the third thing being the soils. So that's sort of things that kind of we thought was really important, and Michelle really highlighted this, and the U.S. folks are way ahead of us in permafrost characterization. But it's of no doubt that knowing where permafrost is key. But finding permafrost, I won't get into it, can be hard for many reasons. So when we're parameterizing or thinking about models, knowing where the permafrost is critical. But it's actually, again, there's different techniques folks have used, but it's still something that we struggle sometimes to properly characterize the disposition of permafrost in these landscapes. I mentioned it. This is one of the original slides I took, because that's an original Leatherman. I wonder where it is, of just these organic soils. No matter where we look in the Canadian sort of subarctic and high Arctic, there's a veneer of organic material. Decomposition is very low, and so this soil I pulled out is probably representative of thousands of years of accumulation. And these have very distinct hydraulic properties. And we spent a bit of time, again, in the early noughts, looking at these hydraulic properties across different sort of environments. Fort Simpson was Bill Quinton, and up in Inuvik, Phil Marsh had a trail Valley Creek, and Whitehorse is Wolf Creek. Just looking at the extreme large porosities of these organic soils, extreme low bulk densities. These are big, giant sponges, which have really peculiar hydraulic storage and release properties, whether it be drainable porosity or hydraulic conductivity. And if the water table resides within these near surface organic soils, it's sort of, you have this kind of responsive system, but it's also able to turn off and become kind of switch on, switch off quite rapidly, simply because of its high water holding capacity. So it's something, again, that I've seen land surface models try to parameterize. I still don't think I would say that the physics of these soils have been properly characterized in hydrological models. They're very sort of unique, and there's lots of room. And we've done lots of lab work about it. And there's papers that we published, putting these things in permeameters and columns, and looking at saturated and unsaturated flow. And it's compressible media. It's not like a soil. So it's something, again, that needs to be considered. And again, when we look at sort of runoff process, it's something that's always ubiquitous across the Arctic and the subarctic, is the idea that there's a lot of preferential flow. There's preferential flow. It's whether it be water tracks, hummocks. Water tracks are famous from up in Tulip Lake, and Bill Quinton looked at hummocks, and I looked at some soil piping. There's always sort of an odd, weird plumbing that's near the surface in these permafrost landscapes that sort of rapidly conveys water to the stream, almost quicker than the rapid conveyance of water through the organic layer. So these are just sort of common high or sort of mid and low Arctic features that are runoff generation processes on these landscapes. So again, these are just sort of different ideas and conceptual models of how we've done these things, and numerical approaches. They're there. They really haven't got much sort of uptake, I don't think, but but there has been sort of a lot of detailed work, and some of this goes back quite far, even into the 70s. There's a lot of papers in sort of obscure Canadian journals looking at runoff processes in Arctic and subarctic landscapes that sort of probably haven't been found. Again, this is just a picture from Bill's PhD of hummocks, and hummocks on the landscape are very common. And again, this affects the tortuosity almost analogously as a groundwater flow and how water gets to the stream. So again, the first one is aspect. The second one is this organic soil. Aspect, again, isn't just affect permafrost disposition. We sort of know it's sort of south as to the north. Here's a nice picture from the tombstones, and you can see some of the slopes melting out that are south facing. We've played around a lot with virtual basins and looking at north and south facing slopes, but it's kind of, as I said, fairly obvious. The sort of more mountainous we get, the more that aspect is really going to play a large influence on our basically timing of hydrological processes. So again, we spent a lot of time just sort of thinking about this. Other folks we noticed picked up aspect in places like Arizona, et cetera, decades after we sort of said aspect was important, again, as I say, because a lot of this literature of northern hydrology really hasn't been picked up because a lot of it was almost pre-internet. Again, this energy controls the active layer development and how water gets to the stream, and different areas thaw out. And there's all sorts of almost laborious, detailed sort of studies of snow disposition and water, kind of celerity and how it moves to the stream. And so this combination between permafrost, active layer depth, soil hydraulic properties, and their variable hydraulic properties with depth is really what sort of is the linchpin or the link between getting water from the landscape to the streams. We started using stable isotopes a long time ago. I call it the dark arts, stable isotopes. That's actually not even a busy fridge. So we have thousands and thousands and thousands of stable isotope data that has tried to inform our understanding of things. And, you know, when we first started looking in Wolf Creek, we really, you know, there's this kind of, is it new water or old water? And these were the paradigms at the time. And we really saw a lot of groundwater that was in the systems that was, you know, and so water ages may have been old. It was storing lots of water. So knowing where the permafrost is in these basins is really important because areas, you know, there was more sort of old water, quote unquote, so the old water paradox than we thought. But so that kind of pushed to permafrost. And yeah, and so no matter where we looked, whether it be ionic constituents, year over year stable isotopes, yeah, there's a lot of storage in these systems. These storage was much greater than I think we initially anticipated. And we started working with some numerical modelers or just process-based modelers. Is worked with one of Dorota Tetzlaff's PhD students, Taya, and she had a sort of tracer-based hydrological model that we use data to parameterize. And the water ages in these basins are not young. I mean, there can be over a year long, several hundred days or longer, and there's sort of uncertainty there. But we're able to show that, you know, even though they have a fair bit of permafrost in these basins, there's a lot of storage within the system that needs to be considered in hydrological models if you're attempting to, you know, represent the system faithfully by calibrating for both flows and to something like a stable isotope. So that's been fairly informative. We've also been using high frequency data. And the one thing I'll say is, you know, it's messy, but the one thing that the high frequency data is showing us is that I think we have a fairly good understanding of our two-dimensional flow system where we have these lateral layers, as I was talking about. But some of the data and the responses when we look at individual events, we sort of see some lateral connectivity, which I'll touch on when we talk about Chris events in these landscape, that isn't very well conceptualized, where, you know, whether it's near stream and away from stream, and how this sort of a lateral connection sort of links up the landscape versus the vertical one. Okay, so again, we looked at, we saw this, and then I had a student, Arsh Ruhl, who's now at Michigan State, and we tried to do something that very few people in sort of looking at catchment process do, and it's basically, as opposed to looking at the outlet, we want to look everywhere within the catchment. So it was sort of a planes, trains, automobiles, tiers tour. I think maybe again that's Tyler was in the what's it called, snow there. And we looked at, basically, we tried to crack Wolf Creek open into subbasins, and each one of those dots is subbasin. And we looked at flows, we looked at salinity, we looked at stable isotopes, we looked at all sorts of things at different times of year. And all we were really trying to do was trying to say, well, how are these basins like internally responding? And do we understand these lateral and connections more? And Arsh recently put out a paper in HP where you can kind of just sort of see that, you know, at smaller scales, less than 50 square kilometers, we have this huge amount of variance. And as we go up, the variance collapses. And this is what we'd expect. But the interesting thing is when we combined this with flows and looked at all the sort of kind of covariates, Arsh used a pretty interesting kind of analysis technique, which we borrowed from Ben Abbott and some other folks looking at how stable these things were time and some classic mixing. And, you know, unsurprising, there was a lot of flow and hot generated in alpine areas where there's more precipitation and less soils, but there was a remarkable stability in these ecosystems. They didn't really sort of act as a threshold that we thought they were, where some areas would link up and link off. And by doing this sort of analysis, it was sort of from a modeling perspective, you know, to keep it simple, there was a really high variability across the landscape, but that variability was very stable. So we didn't see that variance across the landscape change much with time. So we characterized this sort of synchrony and stability. And that was something that we kind of didn't expect, that although there was variance, that variance within the landscape was highly preserved in terms of chemical transport and also with flows. So that was sort of an interesting thing in a mountain landscape to put in the back of your mind that we discovered that may be useful for model application. We apply some of these techniques up in Tombstone. Arsh again started working up in Tombstone, and we collected a whole bunch of, you know, geochemical data and flow data across these 6 observatories and try to contextualize it with Wolf Creek. And again, just to keep it simple, you know, these conceptual models haven't changed a whole lot since 1999. Topography really matters. Weak versus strong topographical gradients obviously make a big difference in flow pathways. And ARCH was really interested in the chemical mobilization of organic carbon and isotopes, et cetera, just to keep in mind, one of the main things we thought was topography is really important. And again, also permafrost extent. This paper is in, I guess, HESD at the moment, it's submitted. So you can probably find it and go in there and read it, and you can post a comment if you like or dislike it as well. I think that's the way HES likes to work. But again, years and years and years, all these different things, it's still permafrost extent and topography really mattering. Again, we've developed a whole bunch of these conceptual models that try to link flows to chemistry and to see how this works. So they're there for modelers to kind of look at and read, much like the ones in the US and Tor Jorgensen's are and Michelle's. So there's lots of things out there to look at. There's a bear in that photo, which I just noticed. We're also looking, we worked with Kieran. I know he was a talk last week, I think, or a few weeks ago, using his storage selection function. So we have a paper, I always say in rejection, in submission right now in water resources research, using his kind of more sophisticated age-based water. And the interesting thing that these results have is that it's in these permafrost environments that are continuous permafrost, the water ages are very small compared to, say, Wolf Creek, which where they would be very large. So it would go from hundreds to thousands of days to under like 50 days, 40 days in these environments. So the storage in these environments, just from a water age and a mobilization of water, is very limited. So again, permafrost again playing a key. Many cold region processes we poorly understand. I think Benoit will probably talk about some of these. Channel snow and ice. I mean, our channel's got lots of snow and ice in it. Here's a picture from the high Arctic where I did my master's. This was the source of water for the stream snow that simply blew into channels and ran off through the summer. I've never seen a hydrological model even try to represent that. That's what this environment looks like, but I don't think there's too much of that in Alaska. What else? Aerodynamics, blowing snow. We see that blowing snow is something that's super critical in these environments. We spent a bit of time looking at how certain different areas of the landscapes are sources and sinks, which really set up runoff processes later in the year. There's a picture of John Pomeroy on the right, and I guess a younger me on the left, in one of our catchments that you can kind of see these shrubs. And some of the big things that sort of came out of all of this was that vegetation and sort of topography and aerodynamics play a really big role in the landscape of trapping snow and having sources and sinks and having certain ecozones be the ones that generate a lot of runoff. And again, we've this is just an old LiDAR. We first flew LiDAR in 2007, sorry, and kind of worked with Richard Esri now in Scotland to do complex wind flow models and sort of see where the snow gets pushed around and just do some simulations to sort of see the impact of wind redistribution on snow and whether we can incorporate those into numerical models. And it's quite important. There's lots of late line snow drifts in large amounts of water that stays on the landscape much longer in positions that aren't aspect dependent, but more aerodynamically dependent based on, basically lees and slopes and where things fall out. Again, sources and sinks in the landscape. Where there's more vegetation, things tend to be sinks. With vegetation, wind speeds, they trap, et cetera, and in areas of the landscape with very little vegetation or with, kind of emergent vegetation, they basically have the snow that's blown off or sublimated or moved. So we've done a lot of work about the geometry of landscape, but also with how vegetation sort of affects things, because there's a lot of water moving about in the winter. We have 7-8 months of winter, right? So there's a lot of chance for water to be intercepted, sublimated, and also blown around into kind of river valleys and lees of slopes. Precipitation is incredibly variable. I don't need to talk about it, but I assume that for most hydrological models, it's needed. In Canada, we have an extremely sparse network of precipitation. This is one of our sites where we're measuring snow and rain independently with like 13 different gauges and instruments. And, this is where sort of dreams go to die when you try doing intercomparison projects. This is just one site. There's typically in these alpine and northern environments a fair bit of heterogeneity in precipitation. That's something that everyone talks about. Everyone knows that precipitation regimes are changing. It's becoming much more convective. And our ability to characterize that precipitation field is really hard. There's no radar, there's no method. So it's something that's just to keep in mind that when we're considering hydrological models, that precipitation, it's going to be hard. Okay, and one more thing. A beautiful picture from the Dempster with some dead vegetation, which I won't talk about. The plants. The one thing that we have seen, this is where I'll sort of wrap up, is that there's a big change that's occurring across the landscape. There's tree line migration. These are just two LiDAR flights, 11 years apart, and this is sort of a shrub over a certain height masks. Where when we first started setting up Wolf Creek, we put towers now that were above the shrubs. Now they're below the shrubs. We actually were so lack of ecological knowledge base that we didn't realize that the shrubs would grow. This is ubiquitous across the Arctic, and it's having very large feedbacks on the snow as we accumulate in these ecosystems simply because they trap it, but also on evapotranspiration and surface atmosphere fluxes. This is the work of Erin Nichols, who's now at the University of Calgary, and she spent a lot of time looking how forests and shrubs and different sort of vegetation assemblages sort of cycled water and energy, and would look at transpiration, evaporation, partitioning, and it's pretty fascinating. Shrubs, they spring up in the snow. It's really emergent. But the one thing that Aaron found is that the surface atmosphere interactions among these different ecosystems, unsurprisingly, is quite different. And so if we look towards the future and more shrubs and more forests, it's going to have a fairly large impact on stream flow and on hydrological interactions. This is just from Wolf Creek, where the forest sort of evaporates more than sort of the buckbrush, which is the high shrubs, which is more the sparse shrubs. So there's a paper in the journal Hydrology which outlines some of this. But what's interesting is sort of when you look at a precipitation point of view, we have precipitation at all these sites. That these forests are in large summer water deficits. They completely rely on snow to sustain their fairly high evapotranspiration rates through the year. Whereas the other sites, this is where the water is generated. So these alpine areas, as they become more shrubby, things may become drier essentially as these plants sort of transpire to a greater potential. And again, some of this work Aaron has done looking at the transpiration rates, and there's paper in journal Hydrology where she scales from different species to the landscape and then looks at the limits that are on these species of what's kind of holding them back from transpiring and what the main drivers of transpiration and evaporation are. So this is pretty interesting work. And the one take home from all of this is that in the Arctic and the subarctic and these northern environments, species really, really matter, and the type of plant really matters. And there has been a whole lot of work characterizing these systems and their impact on hydrology. So there's still work that is sort of NP means not published that we're still working on to sort of look at where plants use water, et cetera, et cetera. But the take-home message is that species matter, that even amongst shrubs, the species are different and they use water differently. And sort of something that hydrologists want to keep their mind on is that the vegetation is probably one of the largest drivers of sort of basin function and kind of complements both, say, topography aspect and permafrost extent, and it needs to be considered sort of thoroughly in models. So that's it for me. And Chris just had a few slides. Chris Spence and I did our PhDs together, had the same supervisor. He got sent off to this environment. I was lucky I got sent to the mountains. Chris got sent to the Shield, where he toiled in a tent just like me for years, and we'd come back and talk about it. And Chris worked to develop a conceptual model that applies mostly to the western part of the Canadian Shield. The eastern part of the Canadian Shield, I don't know if you call it the Canadian Shield in the US, the eastern part of the Shield is much wetter than the western part, but the western part is fairly dry. It's only 300 millimeters per year. And because of this, you have this sort of threshold mediated landscape. You kind of see there's not really big hill slopes, but there's a lot of rocks and maybe wetland depressions. And it's a really heterogeneous hydrological landscape that probably would challenge modelers much more so than the alpine landscapes that I was previously talking about. If you look at the water year runoff and water year precipitation, you certainly see a threshold response there, quite a sharp one actually. But it's a landscape of, I would almost call it Lego pieces, where there's certain sequencing that occurs, and certain sequences have been cut on and off depending on how wet a year is, and therefore landscape response can be extremely heterogeneous. Chris worked on developing these conceptual fill and spill models. Again, below from his work, Spence and Wu in 2003, that's in the journal Hydrology, and basically where different processes on the landscape fill in these soil fill depressions and how wet they are and where the water table is, combined whether they spill over sort of bedrock sills and these things. And so I think Chris was one of the first, at least in a conference perspective, to use these fill and spill narratives and to sort of like in detail with field-based measurements, put together some sort of kind of conceptual model for hydrologists to take from there. It's pretty, as I say, challenging and daunting landscape to sort of look at, simply because it's highly nonlinear. Hawk Wu, and a master's student, also looked at sort of lakes and big lakes and small lakes, and when lakes turn into streams and thresholds. And again, so it's a classic sort of almost, I wouldn't say Nash cascade, but some sort of reservoir routing sort of problem that sort of is very moisture mediated. So this work, again, is something that people that are looking to model large domains, probably to get the processes right, might want to consider. I would not exactly sure how to scale these things, but here's just an example that Chris sent of the landscape, and the blue is a no storage deficit, so wet, and then as it goes to red, it's high storage deficit, as it would change through the year. And in essence, this is the changing of your drainage network as it rains and doesn't rain, et cetera, et cetera. So it's, again, super complex and not sort of easy to parameterize and kind of contextualize, but that's sort of what keeps Chris busy during the day. But yeah, again, it's a really dynamic runoff contributing area that is, again, threshold mediated by how wet the system is. And this applies to a lot of the Western Canadian Arctic, and it all is very homogeneous landscape, and covers a huge swath of continental of Canada anyway, and moves all the way to the east in Canada. The only difference is that as it gets wetter and wetter and wetter as we move east in Canada, the threshold, it's kind of always wet, and it's always primed. So we have much less of this threshold behavior. Again, Chris did a sort of a mixing models and has published these sort of things where you're sort of looking at where the source waters are, and the source waters for hydrographs are highly heterogeneous, where sometimes it's surface bedrock, sometimes it's headwater lakes, sometimes it's this, sometimes it's that. So I think Chris, and when he wrote me an email, he says, I challenge the modelers to model this. So he sort of threw down the gauntlet, and I just sort of put up my hands and said, okay, I'll throw out the challenge. So in summary, and I think the bottom one is the one that Chris really wanted me to read, is that, these subarctic systems are highly threshold hysteretic. They change spatially and temporally, so it's not topography, but there's sequencing and geometry that matters, and which has profound implications for connectivity. And so, for example, when basins are wet, runoff through the stream network can be treated easily as a series of reservoirs, but when it becomes dry, the lakes along the stream disconnect and become just another landscape unit that's not a capacity, needs to be treated as such, with implications for model philosophies, computing resources, etc. So that's all I want to say. Thanks everyone for listening on my iPad here. Hopefully that turned out okay. And all this work was funded by so many people and so many generous collaborators through the years. I can't go without thanking them and knowing that I'm lucky. Okay, so thank you. I will try to unshare my screen somehow and see how this goes. Okay.
Thank you so much, Sean. That's a lot of complexity.
Yeah.
And for someone who spent 30 years in the field and looking at the course, looking at patches of landscapes, it just really tells us the challenge, to simplify. So the floor is open for questions, and please use Q&A. I have 3 questions here. I'm going to skip the first one that was regarding to the previous talk. And I'm going to read the first question for this talk from Hibib Raymond. And did the impact of aspect on catchment runoff change with the seasons?
Mm-hmm. Yeah, I see both questions. I just popped the thing out. Okay, first I'll say Wolf Creek's about 100, it changes in the literature, 180 square kilometers. And the impact of aspect does change through the seasons. Yes, typically the permafrost areas are always sort of the triggers, and the high alpine areas are always the triggers. But when we get into mid or late summer, these permafrost underlain sort of watersheds and areas don't really, provide a whole lot of water late in the year. So there is we do sort of have to treat them differently, and we've done sort of cumulative sequences and water balances, and they have different drivers that promote runoff at different times of years, because simply we have snowmelt, we have precipitation, and then we have frozen ground, and there is frozen ground in the non-permafrost soils, but then it thaws quite quickly. So again, it's a delicate dance that we have to sort of kind of consider. I think we understand the processes, but they do vary, and they're, you know, we have a long-term data, and certainly the winter flows are going up. That's the only thing that would sort of hit the Mann-Kendall test at sort of P point whatever. But in terms of summer flows and spring flows, it's a very high signal, sort of noise to signal system. So we have so much interannual variability because of teleconnections, et cetera, that we don't have a lot of statistical changes that we've observed. The one thing that has been observed, and this surprises people, the other thing that hits is winter flows, and that our freshet, our peak flows are getting later. And that's something that confuses people as opposed to getting earlier. And we're still have a few hypotheses on that, but it's sort of, again, just at the edge of significance over 30 years that it seems like the day of maximum flow is getting later in the center of mass.
Next question coming from Martin. When you drive through the Yukon, you see massive rivers that are fed in part by glaciers. Can you talk about the importance of glaciers in the hydrology of northern landscapes?
Oh, yeah. I mean, I think maybe Benoit is doing a bit of work and he'll talk about this. That the glaciers are sort of the headwaters of the Yukon. They call them the southern lakes, et cetera, et cetera. They're a really, really important aspect of a lot of these major rivers, for sure. Not all of them, but a lot of them. And typically what they do is they sustain a lot of high flows in the rivers late into the year. I mean, if we look at the Yukon River at Whitehorse, which is the only place it's dammed, sometimes the peaks are way out late, like mid-August, early August. So it's this kind of high alpine, massive snowpack that melts really late and sort of pushes up at least levels. I'm not sure what it's like way down at Eagle or where it dumps into the ocean, but it's this real late supply of water. So that often the timing of these headwater catchments that we're studying isn't really in phase with that of the major Arctic rivers because of this kind of glacial contribution, which is very few people. I mean, some people have looked at glacier stuff, glaciology, but there hasn't been a lot of people looking at sort of glacial hydrology in through the years. And challenges are pretty big.
Another question from Kebab Raymond is, what size is Wolf Creek catchment?
Yeah.
Is there a change in the long-term stream flow from this catchment?
Yeah, so I mentioned about the stream flow, and it's 180 square kilometers, and all the Tombstone ones are between say 10 and 30-ish, so not that big.
Is there any long-term stream flow change in this?
Again, just the low flow and the peak, and
Okay.
that's it. So nothing really.
Okay. A question from Walter. Let's talk with regard to redistribution of snow. Would that be mainly happening within a basin or go across topography-based basin boundaries, or both? If it goes across the boundaries basins, can you guesstimate the extent to which that would matter for water balance, or is there too much variability for such a guess?
Well, I guess depends on how big your basin is. So if you had a very large basin, it's probably distributed within basin, but if you have, say, a 10 square kilometer basin, it could probably go out, so I think that's a question that maybe if your domain was large enough in your model, you might not sort of be a process that like the redistribution aspect is that much of a critical, kind of piece of the puzzle if you had 100 square kilometers. But the one thing that it is really important for is there's a whole, when the wind gets going, there's a whole bunch of sublimation that occurs. And again, I'm not sure how large scale models parameterize that, but it could be a significant sort of loss of water through the winter, just if it's really windy and blowing water around. We know that from a long time that it's just, into the vapors. So again, poorly characterized, but it's sort of something that sort of we just know from like mass balances and snow surveys and what have you.
If no more questions lining up, I have a question. I'm going to challenge you, Sean, to give me a list of top processes. When you think of the northern landscapes, what comes to mind is the sun angle is low.
Yeah.
It's windy. It's cold. Right? So the low sun angle tells you that energy, the aspect, really matters. So that was one of your couple first slides. The aspect has to be captured. The north-facing, south-facing slopes are so different. And then, the coldness you mentioned, the soil freezing is a fundamental driver. The depth of the hydrologic cycle, basically, the seasonality. And of course, aspect will affect that. And thirdly, it's windy, right? So the snow gets redistributed, and probably the gauges also miss a lot of snow.
Oh yeah.
So because of the windiness. What else that you think we must put in the models?
I think the one thing, I think permafrost is something that people would obviously get in the, there's things I didn't touch on. I think Michelle mentioned that the geology is really important in getting the geology of these landscapes right. I didn't have time, but it's sort of something we know is, affects a lot of the plumbing of these systems, especially when we combine it with permafrost extent. And again, people know it, but as I said, just sort of the mechanisms and processes associated with this organic soils. Typically people are using Darcy's law, they're parameterizing something like that. I think most of the flows in these things are turbulent almost, right? So it's we're using kind of physics that probably isn't meant to be used for these soils, and I think there could be some more creative thinking going into sort of how we characterize those as we scale up from in landscape. It'll probably go out into some kind of calibration wash, so people may not care about it. But I think that when I'm out in the field, these organic soils behave just so differently than mineral soils. It's like a profound shock when you're in these landscapes. Is that some of the sort of stream flow responses we see, whether it's rainfall runoff ratios, streams becoming ephemeral when it's wet because of their water holding capacity, etc. So that would be
so what we would add on top of that, really the subsurface plumbing systems, really the geology, the preferential flows you mentioned, and the thermal casts that Michelle showed, to capture these highways, those fast paths are really critical as well. And you also mentioned vegetation in the end.
And as I said, that's the last one. People always sort of don't kind of maybe give it its due, but I think in terms of change, I mean, there's fire, there's permafrost, vegetation is just changing so rapidly. And when we started looking into it, it was, again, a first order sort of influence on water balance fluxes in the landscape, not just evaporation, but interception, energy balances, sort of like timing of like long wave radiation. Like it just goes on and on and on and on. It's just how much changes in vegetation will affect the hydrology.
It will play a stronger role as it gets warmer because the biomass will increase in time.
Yeah, absolutely.
Thank you so much, Sean. And let's give Sean a round of applause. And if we have no questions now, we can, if there are any more questions, we still have like 3 to 4 minutes.
Sean, I might have a question directly for you, if you don't mind. I'm trying to start my video here. Okay, here you go. So Sean, I think in Michelle's presentation there was a comment, and I understand it, about burnt area, permafrost will suffer a lot, like an order of magnitude or so. That's crazy. Now what I see with shrubs is that they, as shrubs start to grow on the tundra, now they intercept the snow and fairly insulate that landscape. So is that exactly the opposite?
Yeah, it is. I mean, there were lots of sort of, I think like Robert Way and some folks in other areas that have looked at sort of like shrubs trapping snow, warming the landscape. I mean, is that what you're, and warming the soil and degrading the permafrost? I think that will happen. And I think that, snow, I mean, wherever there's no snow, a lot of times in the Yukon, people think there's permafrost because of something, but really it's just a lack of snow. And that's why it's permafrost. So anywhere that sort of we are trapping more snow, it's even 10, 20 centimeters of snow is a huge insulating factor in sort of warming soil. So I think that's a negative feedback or positive feedback, depending on how you want to look at it. But these vegetation, if you kind of think of their structure and function, I mean, they really win when they trap more snow because they warm it up, they can mineralize more nitrogen. Like there's a real positive feedback. And so this kind of vegetation expansion sort of makes total sense, that these vegetation moving in there, they're making the environment more habitable to themselves, and in the process degrading permafrost and warming the soils. So I'm not sure that's exactly what you're asking, but that's happening.
Okay, thanks.
I think we are due for a 5-minute break, and so we'll come back 5 minutes, and we're going to start promptly 5 minutes later. And
Okay.
if you have questions you never got a chance to ask, please type in the Q&A, and it will be recorded, and Sean will be able to respond to you in the chat box as well for the panel. We'll
Thank
see
you.
you in 5 minutes.
Yeah, hi everybody, welcome back. Benoit, did you want to share your screen as I introduce you?
Yes, I will do that.
Awesome. Yeah, so we're very pleased to have Benoit to COT join us today. It's interesting when you talk to the river forecast centers in the Yukon government and the Alaska Pacific River Forecast Center and ask what's your biggest challenge? It's river ice. It's the power of river ice that's affecting a lot of remote communities in northern environments. So had the pleasure of visiting Benoit in Whitehorse a few weeks ago and learned a little bit about what he was doing. Benoit is a senior research associate at Yukon University in Whitehorse, and he's been doing a lot of work more on the hydraulic side, and really excited, Benoit, to hear from you this afternoon.
Thank you, Martin. So I hope that I can be heard clear here. You can hear me okay. Screen works as well. Okay, perfect. So yeah, so thanks, Martin, for the introduction. So yeah, I'm a senior research professional at Yukon U and also adjunct professor Laval University. This is where I grew up as a river ice engineer and scientist. Just a few words about me. So I did my bachelor in Polytechnique Montreal. Weirdly, I was mostly interested in hurricanes back then, and I feel sorry for all the people in the US affected by Hurricane Helene and recent days there. Quite dramatic event. Yeah, my objective after graduating was to study hurricanes. Then I went to Vancouver for a master's, and then I was interested in sediment transport and channel morphology, and in the end I did this doctorate in civil engineering and river ice engineering actually in Quebec at the Université Laval, and then was stuck in cold region. And this is where I guess I became this river ice enthusiast. And so I've been a researcher now and focusing on actually not only cold regions but mostly winter season for I would say now 15 years. I worked for the private, public, and academic sector, so I kind of understand like what everyone's role is, or that's what I pretend to. I studied river ice processes in a large range of geographies and climate. I was well trained and supported by several CRIPE members, so that's part of Canadian Geophysical Union. Lots of members in Canada, a few in the US as well, including Stephen Daly from CREL, retired a few years ago, Hantao Shan from New York, and Edward Campema, who's also retired. I think I've had a lot of chats with him, and great guy to work with. My favorite quote, and that's something that I've read a few times in reports, that the project should not have any impact on the ice regime, or the ice regime should not have any impact on the project. And that's often fairly lightly written, just to say, ice would be fine, but ice is ice is never fine. It's quite complicated anyway. So so that's what anyways I'm gonna try to talk about today. So the outline of my presentation is fairly simple. So just the roles, some introduction to ice processes. Then I'll talk about types of ice processes, mostly pictures. I'll talk about winter hydrology, focusing on a few processes that have an impact on flows, and landslide and current research. And just to mention, so this is a map of Canada. So I've been trained, like I said, in Quebec City. So I've worked a lot in the St. Lawrence River Basin and tributaries, fairly small creeks to mid-sized rivers. And now I live in Yukon, so different geography. I work in the Yukon River Basin and Mackenzie River Basin. Just because I worked in some of the Peel River streams and rivers. So fairly different, and these are all, of course, traditional territories. I'd just like to acknowledge that I'm here in Whitehorse in the traditional territories of the Tanquachan Council and Kwanlundun First Nation, and we worked at pretty much in all 14 First Nations in Yukon and different watersheds. And some of the pictures I'll be presented are from Quebec, so the Huron-Wendat First Nation as well. So number one, roles and impacts of ice processes. That's a diagram that I've put together like a long time ago. So weather conditions affecting the hydrological regime and the thermal regime of streams. Then there's this sediment transport, feedback loop there with the supply and the morphology. And there's a feedback loop, the morphology affects the hydrological regime. So that's fairly simple. And that's like the warm region, I would say, perspective. Now, if we introduce ice processes, I'd like to put that in the middle. So there's an impact between hydrological regime and ice processes, also the thermal regime. It affects sediment transport. Ice processes, ice pieces can transport push sediment, destabilize, the armor layer. So definitely there's something there. It also, freezes the banks, protects the banks against erosion. Sometimes you have these big pieces of ice that are protecting the banks. You see a few pictures here from a paper from 2017, mud and stones on top of an ice slab on the floodplain. Big stones, this is about 30 kilograms, probably maybe 50, I don't know, it trapped in an ice piece, again, deposited 4 meters high on the floodplain. That big boulder here is actually 1.5 meter in diameter, was pushed after an ice run by about 6 meters downstream. So, that's something that only ice can do. Ice runs will also destroy vegetation, modifies, multi-channel reaches, etc. So definitely there's this feedback loop here between channel morphology and ice processes as well. And that's a model that was produced, I think, in 2013, that is in the reference at the end of the presentation. And if you're interested essentially in, minimum annual flows, maximum annual water levels, year-round discharge estimates, or winter flow forecast, then you should be interested in river ice processes. So this presentation, as opposed to the previous presentations by Sean and Michelle, it's not necessarily about the landscape, but about what's going on in the channel itself and how this affects flow processes. Just flow and discharge. This slide is, fairly understandable. Open water rating curve, which is a relationship that applies to a single location in any given river, hopefully at a stable location. You can see, for example, 2-year flow, 200-year flow corresponding to water levels there in terms of frequency or return period. And what's fascinating about river ice is that there's always backwater, there's always, higher water level for a given discharge. And these are essentially the, conceptual distributions of all these processes, where the data would plot on a rating curve. They plot well above. And, depending on the process that you look at, these are just 5 processes here. You can have, water, you can have water levels much higher than the 200-year open water. I'm thinking about, for example, braided rivers in cold regions. I'm talking about areas where, ice jams are quite frequent. You'll have that. So definitely something to keep in mind here. An example of that is just 1 year of data. You see Q2, Q20, Q100 for the return period at a specific location, and you see how the ice jam data points are plotting close to what an open water, a 100-year open water flow would have created, and that's only one single spring ice jam. This is data, I think, from the Klondike River in central Yukon. Maximum water levels for different processes, so annual peaks for different processes, breakup peak, open water, and freeze-up peaks. And you can see how the breakup peaks are much higher at a discharge that's actually quite lower, estimated discharge, of course. And if you do the statistics of that, you'll see that, for return period, let's say of 100-year, your ice jams are causing water levels that are 2 meters higher than the open water. So that's for the role of ice processes in some areas in the north. And I would say in most in Canada, you could argue that, but this is probably just happening on the Klondike River, but this is probably reality for 30 to 50% of the rivers in Canada, and probably some in the US as well. So that's definitely to take into account. In terms of types of ice processes, if I, I would say there are probably like you could argue there's like 50 different ice processes or different ice types or ice features that you could describe in different streams and rivers. I won't go over 50 of them, but let's just say that there are multiple dimensions or way to classify these processes. You can consider the season, freeze up, break up, midwinter events. Are they in motion or not? The state, is it floating? The ice floats, but does it always float? And the answer is no. The type of crystals, from frazzled particles to columnar ice. The evolution, is it fast? Is it passive? Is it thermal? Is it mechanical or dynamic? Channel size also impacts ice processes. The gradient is also something that is important. Hybrid, usually we consider that the riffle pool is kind of a hybrid river. Low would be meandering and steep would be these rapids or step pools, etc. And climate, we could consider 4 climates here. Again, I wouldn't stick to official classifications, but just to say temperate, cold, which is, Quebec City area. And I'm here in subarctic in Whitehorse, and there's Arctic further north. So a simple diagram that was, I would say different versions of this exist. So that's kind of an introduction. When there's a river ice course for, scientists and engineers, this is one of the first graphs that you'll see. You can see that x-axis either as being a distance downstream of a river or something that you see over time at a single location. And you see frazzle in the water is the first form of ice. There's anchor ice. There's ice that floats to the surface, agglomerates, and produces ice flows, and eventually stable ice cover forms at some point downstream or at some point in time. And some ice could be transported under it. So that's I would say, fairly general diagram. Now, if I present some pictures, the first type of ice that fascinated me was the spray ice, because the water temperature could still be at 1 or 2 degrees Celsius, but yet, if you have a cold night, you have a lot of water that's actually sticking to these rocks and vegetation on the side of the rivers. And, you look at this is only a small creek, but when you think about thousands of small creeks in a large watershed, that's a lot of water that stops moving all of a sudden. It's not flowing downstream. So you can consider that this is a freeze-up process, stationary ice, non-floating, because it's fixed to the banks. It's a gradual process, mostly in steep channel where you have splashing, and pretty much any cold climate you could probably see that down in Texas in some cold nights, and of course further north in northern Canada and Alaska. Frazzle, sorry about the picture. That's probably the only picture that I've ever took about frazzle. This is a aquatic camera, nothing fancy. You can see some ice flocks there, but small particles as well. So this is something that some river ice researchers are just focusing their whole career on. All these particles and how they are either active or passive, meaning that active they stick to the bed, and passive they actually just drift or float to the surface when the water is at 0 degrees Celsius. They're actually active when the water is slightly below 0 degrees Celsius. The temperature is slightly below 0 degrees Celsius, so that's called supercooling, and this is when you have a lot of frazzle production. Anchor ice, so part of this frazzle can stick to the bed, so that's again an aquatic picture. Say it's a porous ice mass there. That's also ice that stops moving. It's anchored to the bed. Eventually it can float away, but on this picture you can see it's staying there. And you can have massive accumulations. You can have meters of accumulation of that type of ice, and of course the water level in those creeks rise as a result of that. Again, by many centimeters to many meters. We've evaluated that the rise in water level caused by anchor ice and ice dams is in the order of 0.5 to 2 centimeters per hour. So that's a lot of water again stored in a lot of those creeks that doesn't flow downstream. So from above, from a little bridge, you can see how the bed of a river can become all white. You have these emerging ice forms that are not floating. They are anchored to the bed. You can call that icing or off ice, depending on your where you come from. And this is typical of a freeze-up process happening in any rapids, step pool channel. Very fascinating, and this is actually the way that the river or the stream manages to create its own ice cover during winter, because you could look at these rapids and wonder how this river will freeze in winter. It actually does, but it needs these ice dams and anchor ice in order to do so. And I'll just present you know, closer look here of an ice dam. So you have icing layers on the side, anchor ice in the middle. That's after a midwinter rain on snow event in the stream and close to Quebec City. And this is probably the best video that I have about how these creeks form an ice cover. So hopefully this works and you can see it. So this is 30-minute pictures for a few days. I would say 6 days of the video lasts. And we were fortunate to have the moonlight. So you can see ice dams forming, anchor ice, and you can see how it rises over time. It snows, but then the water rises and takes the snow and becomes part of the ice cover. And yeah, so you can see that now the channel is actually at bank full, and it's at very low flow. And the process ends like that. So you have essentially, you know, a normal freeze up cycle on this little creek there at a discharge of, let's say, 0.5 cubic meters per second or something in the order. It actually reaches the bank full height, and you have a lot of water stored during that event, and the water is actually released, and you have that partial ice cover that is free spanning afterward. And if I show you that in maybe a slower motion in this diagram, so initial condition with no ice, you have spray ice when the air temperature is below 0 degrees Celsius. Then you start to have anchor ice and these ice shells that are start to forming, yeah, some icing or off ice in cold surfaces. Then you have proper ice dams where you have a series of dams and pools. The water velocity slows down, and eventually you have surface ice cover forming. And that's the maximum elevation. And eventually you have, you know, an inversion if in the heat budget, and the whole thing gets perforated from under, especially if you have warm groundwater. So anything that is, you know, warm groundwater, meaning, you know, 2 degrees Celsius or more, you'll have this process, this kind of melting process taking place like very quickly. In colder regions where there's actually maybe you know, groundwater close to 0 degrees Celsius, that could take a while or actually never happen, and then massive off ice will result, and I'll present that a little later. So this is essentially the midwinter state. Spray ice shells can continue if there's open water after that. The midwinter state of a steep channel looks like that. So essentially you have, you know, in cold regions, I would say temperate and cold climates, you'll have that kind of free spanning ice cover. That gallery here on this picture is probably like 50 centimeter high. And the water just flows actually freely on the bed and is not necessarily in touch with any ice during the entire winter season, which is quite impressive. And that creek is actually well insulated for the rest of the winter. If you talk about now lower gradients, border ice and brash ice, which you can see here on a river near Quebec City. So this is something that you'll see in any cold region at the beginning of winter. Floating ice, drifting ice in the middle of the channel, and stationary ice on the side. Eventually, you'll have this bridging process, which I'll show in a second. This brash ice in the middle of the channel can actually become ice pans. You probably heard this pancake ice concept. I call this more like pizza. It just looks more like a pizza than a pancake anyways, but this is the typical shape of ice flows drifting and bumping into each other and becoming quite round with that crust on the outer rim. And eventually this ice drifts downstream, gets to a slow flowing section, freezes in place, and then the frontal progression of the ice cover starts. So that's quite dynamic actually. And if I show a picture, again, that's from Quebec City, but it happens on big rivers in Yukon as well. It's just easier to capture with satellite in Yukon. But so that's again about 4 or 5 days of you know, 30-minute pictures, and you will see the water level rising. and eventually the ice cover forming, and then the following night, you know, you have again very dynamic. You know, it's kind of a battle between the water and the ice there. There's fast flowing water, so it's not easy to form an ice cover, but eventually you'll get a full ice cover for the, you know, most of the winter season. In winter, you can have a smooth ice cover, typical of slow flowing rivers. Usually there's this publication, I would say the most recent publication I've seen about the maximum ice thickness in rivers and lakes is from Debicki et al. 2021. You can see that, of course, it extends to Alaska, it extends into the United States, down south as well. So definitely this doesn't stop in Canada. Ice thickness is mostly you know, in Yukon in the order of 0.75, 0.9, 1 meter near Old Crow, which is our northernmost community. But the ice cover is not necessarily always just growing thermally. You can have a very thick ice cover just at the beginning of winter. So this is a freeze-up jam near Carmax in Yukon. So that's fairly dynamic. This is probably when there's weather instability during freeze up, and there's a good chunk of the ice that actually starts moving. The ice cover starts moving and crashes into a downstream ice cover and creates that, you know, roughness. And the surface roughness that you see is probably the same roughness underwater. So of course it creates a lot of backwater as a result. In riffle pool rivers, you can often see this U-mocked ice cover. So hills of, you know, deposited frazzle and ice, and the depressions are probably where the ice is the thinnest, and where the water under which the water is still flowing. So kind of a dangerous environment, just like the free spanning ice cover that I showed earlier. Of course, there's a lot of, you know, ice thickness on this picture is probably in the order of 1 meter to 4 meters, depending on the location. Off ice, stream off ice. So this is more of a subarctic, I would say subarctic process, Arctic as well, but you kind of need water throughout winter in order to get it thick. So in fairly small creeks to fairly large rivers, this can happen. Essentially, it's just overflow in winter, and of course, this water is exposed to cold weather. It freezes layers. So in layers, off ice is a German term that actually means water on top or ice on top. So it's successive overflow and freezing. And that's a fascinating process that we're studying here in Yukon. This is in a landscape that Sean is familiar with. That's Tombstone Park in central Yukon, just north of Dawson City. When it breaks in the spring, you can actually see that it's really formed of different layers of thermal ice that froze at different rates under different temperatures. Sometimes there's snow layers trapped in that, porous layers, transparent layers, very you know, very thick total, and you know, it's slow. It melts quite slowly in the spring as well. This is another picture from a colleague here. You know, in these orange creeks that you see in the Arctic now with the thawing landscape, this process can still happen. And this picture is interesting because we had this off ice actually, you know, was under pressure, pressurized flow that actually managed to break the ice cover in pieces, just with the pressure of, you know, passive flow, which is quite impressive. So these dynamic processes, you know, can occur in some specific locations during winter. So a diagram of off ice is to explain how it works. You know, again, initial conditions with no ice. You have the normal freezing process of any, I would say, shallow creek with the anchor ice and the surface ice eventually forming. Then you have this potentially this stable ice cover, complete ice cover state. As the ice cover, though, if there's limited insulation, let's say that there's no snow and there's really cold temperature, or the snow was blown by wind, then the ice cover thickens and chokes the flow, and then you have a pressurized condition, and the water will try to escape either through cracks in the ice or through the banks and just flood the ice surface. And of course, flooding the ice surface will just create more and more icing. At some point, you may have a moment in winter where there's this free spanning state. So the water level drops, the discharge drops, but eventually, if the discharge increase for any reason, you get more icing. And if you pay attention, the bank can actually rise. You have like this ice forming in the banks, and the banks are actually lifted up with the vegetation and all that. That's something that we have observed, and others have observed that as well in small creeks and small rivers in Yukon. So breakup is I would say probably the most interesting period for most river ice scientists. You can have a thermal breakup under consistent freeze thaw cycles and low runoff, so the ice cover mostly melts in place, and the limited rise in water levels. So this is, I would say, better for people, less exciting for scientists. Or this mechanical and more, I would say, interesting process, which is when the ice cover is very resistant when it's mobilized by the increasing flow. So that causes a significant rise in water levels and ice jams and ice runs, which I'll show in a second. So how it works from a force perspective is that you have a resistance, the ice resistance, which could be roughly estimated in winter and fairly forecast. I would say it's probably easier to forecast the reduction in strength of the ice than to estimate the initial condition of the ice. And the driving force, it's, I would say, fairly easy to estimate over time, but very difficult to forecast. You have these two lines, and when they meet, this is when breakup happens at a specific location. But then, as I said, you have uncertainty here. At a current date, you have an uncertainty in the flow forecast. So therefore, you have an uncertainty in the breakup timing and as well as the breakup intensity. So if breakup happens at a very high resistance, water levels will be quite high, and the breakup is considered as dynamic or intense. And if it happens very low, then breakup is I would say good for people living close to the river, but there won't be any ice jams or interesting data collected for us. How breakup looks like a thermal breakup from the air. So this is taken from a plane. You can see the ice degrading in place. If you can see my mouse here, this is a small ice jam. So the water is flowing from right to left here. So very gentle breakup, just like on a lake, essentially. If you have more dynamic scenarios, this looks like that. So that's a proper ice jam. I would say, the more wood pieces you see on an ice jam, the more intense breakup is, just because ice can recruit, more log jams and wood pieces and on the floodplain and bring them in the river. This is just an illustration here of an ice slab on the side of an ice jam. So you can see the thermal ice, the columnar ice here, because it's really transparent. You can tell that this breakup was quite dynamic. You have the snow ice layer on top. Usually back east and maybe where there's more precipitation in winter, you have a larger ratio of snow ice compared to columnar ice. But in the northern dry areas where it's really cold, when winter is really cold, you can have that ratio of dominance of columnar ice right there. Spring breakup, very mechanical scenario here, 40 miles just downstream of Dawson. So that's from not this spring, but the previous spring, major ice jam. So that's how a major ice jam looks like. And from the air, you could say, well, I don't see much. Maybe I see some overflow here, but if you zoom out, you have these historical buildings at 40 Mile with water mostly up to their roof, some of them. So that was probably a 100-year ice jam event just downstream of Dawson in 2023. Again, something that the river could hardly produce with open water conditions only. For those not familiar with ice jams, this is a static, static process. Let's say this diagram applies to a small, small river. You have upstream and downstream. So you consider this downstream portion of the jam as an ice jam toe. You have an equilibrium section. The equilibrium section in rivers and small rivers like the Klondike River can be maybe 500 meters long. In the Yukon River and large rivers in Alberta, maybe in Alaska, and Yukon River in Alaska, you can have ice jams that are, tens of kilometers long. And you have the head of the jam, which is where more ice can accumulate. It's mostly floating. It doesn't necessarily contribute to the flooding itself. And you can see the pre-breakup water levels, that blue line, and the backwater associated with the jam is that red line here. And you can have like grounded ice flows, which is typical of shallow rivers. Quite, you know, this happens quite often when the ice cover is really thick compared to the flow depth in the river. Upstream, you have this backwater area. It's ice-free, but you know, upstream, immediately upstream of the, you know, of the ice jam, and maybe some kilometers upstream, you can still have the influence, the backwater influence of the jam. So it's still ice affected over a certain distance, depending on the gradient of the river, and of course, flow bypassing the floodplain, the jam on the floodplain. So this is typical. This is the way nature works. This is how, you know, sometimes it's beneficial, as Michelle said earlier. This can actually contribute to sending water on the floodplain and affecting permafrost eventually later in the season. When an ice jam releases, it causes an ice run. So that's from Old Crow, Northern Yukon, just to show you how dynamic this is. This is not the most dynamic, I would say, possible ice run, but sorry about the sound. Sorry. So it was, anyways, it was windy. Sorry, that was a little loud in my ear. So hopefully it was not too much for you, but you can see all these ice pieces rubbing against the bank. And this is the release of an ice jam from upstream of Old Crow. That ice run can last for hours. It carries a lot of water. Before that ice jam release, the flow was probably in the order of 500 cubic meters per second. And during that ice run, it was probably in the order of 3,000. So it does carry a lot of water. Just to mention that, you know, I'm talking here about ice jams and ice runs. There's this great database from the U.S. Army Corps of Engineers, and it really shows that ice jams are, you know, fairly common in, you know, all of, you know, northern United States, of course, in Alaska. Last time I looked, there was about 26,000 reported ice jams anywhere, you know, in the US. So definitely these processes are happening at a large scale, not only in Canada. Of course, in most areas of the US, you will have these midwinter breakup events as well that will cause maybe more damage than the spring breakup itself. So that's something to consider as well. And, you know, the most important piece of that, I think that, you know, we're all interested in what's the impact of that on the hydrology. I think I've touched a little bit, but if I just, you know, spend a few slides here on you know, flows. So these are, you know, typical hydrographs from, you know, temperate, cold, subarctic, and Arctic rivers. The dashed line is just to mention here that if you have glaciers in your river, you know, flow will peak later in the summer, and there will be greater contribution. But overall, you can see the winter duration from 3 to 4 months to 6 to 8 months, even more. Degree days, so this is CDDF is for accumulated degree days of frost or freezing. So this is in degrees Celsius. So you just sum up all the negative temperature from winter. And the ice cover thickness of a floating, you know, floating ice cover on rivers and lakes. This is probably the order of magnitude. Again, it's rounded up, you know, just for simplicity, but you have very different regimes depending on where you are in terms of degree days of freezing or the duration of your winter. Now, if I look at, you know, over time, over a winter season, how, you know, the stage or the discharge evolves. So that's a kind of the simplistic or the naive graph of, you know, thinking that, okay, you know what, when the ice forms, the water level rises, and when the ice goes, the water level just drops. And in the meantime, the discharge is just following this recession because let's say there's no precipitation, there's no snowmelt runoff until later in the spring. So again, this is very simplistic, and people presenting that, you know, it's not reality for different reasons. This is more of a typical water level signal. So in green here, you can see a drop here in the level, then an increase, and then a drop again. There's instabilities, and there's all these oscillations in the spring as well. And all these can be names, and this is some exercise that we've done here at, in our research is, trying to define like what this represents. So here, this is called a freeze-up depression. So that's water stored upstream of your hydrometric station. This is the rise and freeze up. That's a local process, and that's another second bite or depression in the flow. You have winter instabilities that are probably flow related. You have an ice jam, stage up and a stage down, and after that you have a bunch of waves. These are unimpeded ice runs, so this is actually real flow. And basically what I'm saying here is that there's a need in those water level data sets. There's a need to distinguish local hydraulic fluctuations caused by ice processes from watershed scale that are either caused by runoff or ice processes. These watershed scale hydrological variations are real, and they probably explain most of the variations on the stage signal for a given winter. And no known hydrological model considers in-channel storage cycle. And that's something that, as a community, we should work on quite seriously, because they can impact, discharge estimates, as Martin stated it. So if you think about ice-induced water storage and release events, of course, the ice is some, stationary ice is called ice storage. So that's water that doesn't flow downstream. The roughness or the blockage caused by ice jams or an ice cover, this is called hydraulic storage. And of course, as a stage rises in your river, you have water going into the banks or in groundwater, and that's slow hydraulic storage as well. So this is all water that is removed from the flow that reaches a downstream hydrometric station. And of course, it applies to upstream reaches, but as I said earlier, it applies to all tributaries in the drainage system. So that can be quite significant. I'll show just this simple graph. Well, simple depends on how long you look at it, but in gray it's the energy budget, and in black is the air temperature. And you can see, well, it's varying a lot. So the heat budget was calculated with, using a bunch of equations. And here on this graph, you have the water temperature in black, and the double line is the water level. And you can see essentially, you can see 6 cycles where you have a negative heat budget and you have ice formation. These are ice dams. And every time they rise, they store water. And every time they melt partially, they release their water. So you can imagine how downstream water levels can be impacted, and same thing for the discharge. If I zoom in on some, on this graph, just on one event, you have Irene, I think you have your hand up. Does that mean something? Sorry.
I'm very sorry to interrupt, but just the hand raise was to let you know how much time you have left. We are running out of time. So this is the time for the questions,
okay.
But since we have not yet received any questions, feel free to continue until we get the first questions.
I'll be done in about 5 minutes. Thank you, Irene. Sorry for that.
Thank you. Sorry. I'm sorry. Thank you.
Okay. So you can see that the water level rises and the discharge drops in the stream, and that's a second order stream. And in the third order, you can see this discharge depression caused by all the upstream storage. And when this ice dam releases, you have a rise in discharge as a consequence of that. And on fourth order stream, so that's a freeze up process above. Now in midwinter, you can see how this discharge Q varies with air temperature. So every time there's a drop in temperature, there's a drop in discharge as well. So these are oscillations that are real, they're discharge, and they're reacting to air temperature fluctuations. My most important slide is this one, just to explain it a bit. So these dots are measurements, discharge measurements. The green is the application of the rating curve, open water, so it doesn't apply to winter. And this is the estimated discharge with the existing procedure of the federal government, Water Survey of Canada. And this is our new procedure in blue. So you can see the difference here. At freeze up, we have a 100% difference. And if you zoom on breakup, You also have this different interpretation. So the red line is kind of a daily average flow, whereas we're looking at maybe a 30 or 10-minute flow estimation. You have all these very real flow oscillations that, depart from the red line by, again, maybe 100%. So this is also something to keep in mind. So why do we need accurate winter flow? Well, to determine the water level, the water availability in real time, to make accurate discharge forecasts, make accurate breakup forecasts. We also need great data to document and simulate realistic ice-induced water levels for the design of structures, either real-time or historical data. To have a complete record, this is also important, and to simulate climate change. I mean, if we're not sure what's the discharge at freeze up and break up, how will we, document the impact of climate change exactly? So this is why, maybe we need to revisit some of those historical hydrographs and to put more thoughts into them. And yeah, most data users assume that winter discharge estimates are accurate, which is not necessarily the case. And my last slide is this one. So what we've been doing here at UConnU, so translating complex river ice processes, concepts, into accessible science, improving winter discharge estimates in streams and rivers, forecasting breakup timing and intensity, understanding weather controls on off ice. So there's a research project now going on off ice on along two transportation corridors in the Yukon, mitigating ice-induced floods, and quantifying the impact of climate change on ice processes. And references with hopefully links that can be shared. And yeah, thank you for that. Thank you for listening.
Thank you, Benoit. That is amazing. I'm probably not the only one who just absolutely knows nothing about how river ice works. This is very, very eye-opening. The floor is open for questions. I'm going to read out the chat. Excuse me. Here, the first one is from Martin. Benoit, great presentation. Thanks. You used to be responsible for hydrologic forecasting in the Yukon government and continue to help the Yukon government during breakup. Can you talk a little more about the vulnerability of northern communities to flooding, how hydrologic predictions are used to mitigate and manage these vulnerabilities, and how future advances in monitoring and modeling river ice can help communities deal with changing flood hazard?
That's a long question, Martin. Thanks. I'll try to answer as many pieces I can. So yes, I was a forecaster, and yes, I keep helping a little bit with the the government when needed. I would say that half of the communities in Yukon are probably half of the communities located close to a river are more susceptible to ice jam flooding than open water flooding. Okay, so that's one first thing. I would say that how this forecast can help, we cannot move buildings. We can definitely inform people. People can move their belongings to a higher floor. They can move their cars. They can move anything that they can, and this will significantly reduce, the damage associated with these ice jams. When we visit communities, just before a release from the government saying that breakup could be dynamic, and we see all these vehicles and all these belongings on their front yard, we think we didn't do a good job. So definitely there's a risk reduction just there. Just be if the forecast is accurate, then we can reduce, save lives and reduce damage. I would say that one thing that we try to see is when ice will move and where ice jams will form. So ice jams form usually at typical locations year after year. So this is something that we're studying. Now it would be quite beneficial to know what flow we can expect at breakup. So definitely hydrological models that can simulate how the flow will evolve in the next few days, that can help. If we think about the Klondike River, if the forecast is for, the river flow going from 100 cubic meters per second to 150, we're fine. But if it goes from 100 to 300, we're not fine at all. And I would say there's a feedback loop between the the flow or the runoff forecast and the actual flow, because at some point the flow will reach a threshold when ice starts to move in the system, and that applies to any river in ice affected rivers in North America. As you reach that threshold, you will get some flow instabilities, and so this is something that needs to be discussed seriously, because you cannot necessarily assume just a flat hydrograph or a gradually rising hydrograph. At some point, you will have significant variations, and you could have easily double the flow that you expected because of an ice run, and that ice run will carry a lot of ice and water. And if it jams at some place, it could cause flooding. So definitely something interesting to keep in mind, and illustrating how there's a need for hydrologists and river ice folks to start properly working together. So hopefully I answered most of your questions, Martin.
Next question from Walter. Very nice talk. Thanks. What sort of information would one need to predict ice jams and resulting flows? And at what sort of lead time is predicting this possible?
That's a good question. I would say lead time depends on your depends on your watershed and on your knowledge. If you talk to people in communities, if you look at satellite imagery over a few years, you'll be able to see how breakup usually unfolds. You'll be able maybe to identify anomalous years where breakup was more dynamic than usual, years where breakup was more thermal than usual. And then at some point, once you know your river, let's say with 10 years of data, you're starting to know your river a little bit, especially here in the north where we consistently have a cold winter. I would say, and maybe down south you have more, you have different scenarios, but eventually the idea is to identify dominant ice jam locations, identify conditions under which they form, in terms of, it could be in terms of weather, it could be in terms of flow as well, if you have reliable data. Of course, hydrometric stations are often ice affected, so that's a little challenge. But I would say gather as much spatial data as possible, look at as many years as possible, and just try to understand the process, and that's the first step towards modeling, modeling and forecasting. But generally, I would say here in Yukon, we can see breakup happening probably within a week, but ice jamming, very difficult to see it happening. If you have dominant ice jam locations identified, you could have maybe 2 days, 3 days, but very difficult on most of our rivers. But it can be even more challenging at some locations, quite unpredictable, or maybe more predictable if you're lucky.
I have a question. What is the state of science in simulating river ice? The mechanics of it is so complicated, and it's so dynamic. The Navier-Stokes equations don't even work.
Yeah, that's a good question, Ying. I would say there's a few schools of thoughts there. I would say most models are either static or dynamic, but I would say that when you think about an open water model, you have your roughness calibrated, you have your flow, you'll have your water level. When there's ice, you have to calibrate the roughness of the ice. You have to calibrate, essentially, in most models, you'll have to impose where the ice jam is and how long it is. This is not something that the model will tell you. I would say I know very few models that can simulate breakup happening, and then causing an ice jam at a specific location. This is, in most models, you will have to impose what you want the model to tell you, which is not ideal. So I would say this is the state of knowledge as of now. There's definitely approaches such as what Karl-Erik Lindenschmidt at University of Saskatchewan has been promoting for years, which is a Monte Carlo approach that you simulate hundreds or thousands of different ice jam locations, flows, ice jam lengths, ice jam roughness, several ice jam parameters. So that's one approach. Is it state of the art? I would say I like this approach for some sites. For other sites, it might be, I would say it might be a stretch. People like scientists and engineers prefer to really look at, simulating a specific ice jam based on maybe 1 or 2 years of documented water levels and ice observations, and that's also a defendable approach. But yeah, in terms of forecasting in real time and forecasting the flow and the downstream consequences of that, I would say we're working on it as a community, but we're not there yet.
Thank you for that answer. And I don't even know if the next gen, if the national water model has any ice, river ice in it at all. So we've got a long way to go. And I think if I don't see, there's one question from Martin. Can you comment on the extent to which operational forecasting groups use mechanistic models to predict ice jams? My understanding is that the most operational centers base their guidance on ice jam flooding on observations on the ground from airplanes and from satellite.
Yeah, that's a good question. I would say, Martin, when I was in Quebec, things were mostly reactive. I think that researchers were informing the government and municipalities. I don't think that the government of Quebec has yet moved to include ice jam forecasting in their hydrological forecast platform. I'm not sure how BC works. I know that Alberta is probably ahead of everyone in Canada in terms of forecasting ice jam floods and all that. And yes, they rely on cameras, they rely on water levels. If you look at water levels at different hydrometric stations, you're able to see how breakup is unfolding. People use radar sat, constellation, imagery to inform about ice conditions. This is happening on the Peace River as well. There's a lot of different tools. This is not uniform. In Yukon, there's flights, there's ice maps, there's ground observations. And I would say we do our best to forecast when breakup will happen and at what intensity it will happen. But yeah, the uncertainty is quite high. I would say even if we have a nice, a reliable flow forecast, the uncertainty of how the river will manage that ice, this is still complicated. But as we study, we get more knowledge, and as we get more knowledge, we increase our ability to forecast accurately.
Well, Erin asked me to stop here, but I would like to fit in Michelle's question. Would you think earlier spring warming correlates to a higher probability of ice jam flooding that is breaking during a time with thick resistance ice, or a lower probability of ice jam flooding?
Michelle,
with more gradual warming and melt.
Yeah, I would say, Michelle, I'll try to answer that shortly. In theory, an earlier warming would mean more dynamic breakup because the sun angle doesn't change with climate change. That being said, I'm still unsure, and I think you've mentioned something similar, Michelle, that when I look at ice jam floods, we can see that maybe we're getting into more dynamic in some river systems, and other river systems where actually we seem to be getting less dynamic, but one extreme event is just enough to get us, back on the, on the models, simulation and trying to understand what happened and all that. So I would say in theory, yes, it could become worse, but in practice, we don't see a clear signal yet.
There's one more question, and from Anthony Prussell, I'm going to ask Benoit to answer by probably offline. We are running out of time. And we're really coming to the end of the morning session. And I want to really thank the three speakers with their wonderful presentations. And I must say, these presentations are not easy. We didn't ask them to talk about their own work. We asked them to provide a high-level synthesis of what we know, what we don't know, but ought to know at the community level. So you can see they distill their, decades of hard field work to simplest concepts. They look at across the board, not just their own studies, and to give us that sense of community knowledge. So these are not easy talks to prepare, and then they really gave us a great place to start for the afternoon session. So I would ask everyone to give them a round of applause and really thank our speakers for their time and effort and delivering these high-level talks. And we're going to take a 1 hour break, a little bit more than 1 hour. We'll come back at the 2 o'clock for the afternoon session. For those of you who plan to come to the afternoon discussions, breakout discussions, please register. And Irene had put the registration link to it. You will, after you register, you'll get a link to join in the afternoon session. So have a nice break, and we'll see everybody back at 2 o'clock. Thank you. Bye now.